Hi, today we are going to talk about mathematically guaranteed C and C++ code. We are going to see on a small example as well as a real-life example how it's possible to embrace all the possible behavior of your software, whatever can possibly happen in the environment of your source code. So, we are going to do like a lot of tests. Yes, we are going to do exactly this number of tests on a regular computer. First, let's try with a small example. We are going to consider the scissors cipher. It's a very naive and simple algorithm where actually you just apply an offset to all the letters. Typically, if I have an offset of 3, it means that letter C is going to become F, letter A is going to become D, or letter E is going to become H. First, we are going to look at our existing library and see how we can perform two tests. So, first, let's have a look at the files. We can see that indeed have the implementation in Caesar.c, have the header file in Caesar.h, and my main test driver in main.c. So if I look at Caesar.h, I have two functions. First function here is Caesar encrypt. It takes a pointer to a buffer and an offset to apply, and it returns the encrypted buffer. And we have the function Caesar decrypt, which does exactly the opposite. So now let's have a look at the implementation. More Caesar.c. We can see that here we have the computation of an absolute value function. If x is below 0, we return minus x, otherwise we return x. Then I have the Caesar encrypt function, takes the pointer to the buffer, the integer. I compute first the absolute value of the integer. I allocate a buffer of size 33, and as long as I'm not at the end of a string, I keep the space unchanged, and I add shift to the value, to the current character. So hopefully it does what it's supposed to do. And here I have Caesar decrypt, which does exactly the opposite, because here I have a plus sign and here I have a minus sign. So now let's have a look at how I'm testing this library. So more main.c. This is the way I perform one test. So I basically call Caesar encrypt, Caesar decrypt, and I print like stuff in the middle. Then my main function is I get a random buffer here, and I perform one test with gentest and with the offset -3, and here another test with the offset +7. Okay, so now if I want to test that if everything is fine, I'm going to compile those two compilation units and run the results. So indeed, here I got the first encrypted string, and indeed the difference between P and S is 3. And for the second test, the first letter of the clear buffer is people of P, and the now we can run the test for real to see what happens. So I'm just going to type make, and indeed we can see the results of the two tests. Here the first test, test 1 with the offset -3, we can see that the difference between P and S indeed is 3. And here we got the second test, and we got the difference between P here and W is indeed 7. So everything looks fine. So now what we are going to do is just replay those two existing tests in the analyzer. So the way to launch the analyzer is exactly as simple as linking your different compilation unit. So you write simply the list of compilation unit, and instead of calling GCC, you call this analyzer. Here I use a graphical user interface version. For this reason, it launches locally a web browser. So I'm going to connect on my web browser, reload my page to see what's going on. So I have like one window here on the left, one window on the right here where you have the original C code, the one that we just saw together. So in the middle window here, it's like almost the same code, but it's decorated. You got some color, the code is clickable, and some extra comment had been added by the analyzer itself. And here on the left, you would find a kind of a summary of the issue which were found. So let's look at the two issues which are being reported by the analyzer. So here we have an issue because actually the value buff might be not a valid pointer we could address. The other issue here is that buff plus I is not a valid memory location. So in order to understand what's going on, first let's click on buff. We can see here in the bottom panel that indeed buff is equal to two values. It's either equal to null or the result of malloc. So indeed, if it's null, this is the reason why the first here assert was present. If we want to know actually where buff was created, so where the memory location where buff points to has been created, we can right click on buff, click on show defs, and here is going to tell us indeed that it has been created here at that line. It's fairly easy because in this case it's a small program, but even when you have several hundred or thousands of lines of C code, we are going to find where each and every memory cell has been allocated. So now I'm going back to its original location, so I understand that indeed it can be a buffer, and it was a buffer of size 33, or it can be null if malloc fails. So first issue, I forgot to test that buff was not null. And second issue, here buff is a buffer of size 33, so we should address it between 0 and 32. If I click on I see that I here in the bottom can be in the range 0 to 33, which could be an issue, which is an issue because definitely I can't be over 32. So we just completed actually the stage 1 of using TrustInSoft, because what we have been doing is we have been using it by replaying dynamically the existing tests in TIS, and because of that we find some issue. Now we are going to switch to stage 2, where we are able to boost the coverage of the test with generalized input. What we are going to do here is we are going to extend to 2 to the power 64 tests. So how am I going to do that? First, I'm going to shut this version down. I assume that I corrected the issue we found previously, so I'm going to switch v2, a directory where those issues have been corrected. I'm going to show to you what we did before with main.c. So you remember we did two tests, one with -3, the other with +7 right here. So how we are going to extend the coverage is fairly simple. What we are going to do is we create a local variable named usershift, and here we have a magic keyword named TIS make unknown for TrustInSoft make unknown, where we provide two arguments. First argument being the address of usershift, and second argument being the size of usershift. And basically what this command does is that it actually tells the analyzer that there could be any possible value in user shift. And by any possible value, we mean all possible integer, not a random integer, but all the possible values between the minimum integer and the maximum integer. So actually, at that point, user shift becomes an interval. Even though it's an interval, we can use it and as if it was a real value, and we can pass it to a function. Now I'm going to launch the analyzer, and the way to launch the analyzer exactly the way we did it before. Now it's finished, so it means we just did 2 to the power 64 test. I'm going to reload my graphical user interface, and we see that we have one undefined behavior. So it looks like this undefined behavior comes from the absolute int function here, and I can have an issue if actually x, I could have a sign overflow, and minus x should be below this big number, otherwise I have an issue. And indeed, this is because on computers I have more negative numbers than positive numbers. Typically with 8-bit numbers, it goes between minus 128 to plus 127, so you can't compute minus 128. This indeed is an undefined behavior, exactly like a buffer overflow is an undefined behavior. This is the result that we were able to get, but we are going to do even better. Now, let's assume that I fixed the bug. I am able to know that for the buffer I choose, then it's good for any possible offset. Now, I want to do better. I want to test for any possible input buffer up to the size of 38 for the size of the buffer. So, this is the big number I showed you at the beginning, and the way to do it is like super simple. So I'm going to shut down this version. I'm going to assume that we corrected the issue. I'm going to switch to V4, the version 4. I'm going to show how we can test for any buffer. It's as simple as writing one extra line. The way to do it is actually for the fourth test that we are going to do, to call thisMakeUnknown a second time, but this time we call thisMakeUnknown on the buffer itself, on the buffer str, with the size of the buffer, which is 38. And now I don't actually test for minimum integers. This is why here at the test, if user shift is not equal to the minimum integer, in this case, with this call here, I'm going to test with any possible input buffer and any possible offset. So I'm writing still the same command line. Now I just did this extraordinary number of tests we said okay we would do, and I'm going to reload the graphical user interface, and indeed is good. We have only green checks, so it means that we have a mathematical proof that for any possible input buffer up to a size of 38 and any possible offset, this wonderful Cipher library has no undefined behavior. So you could say, okay, it's nice, but it's kind of a very small example. So for you, I got some real world example. First one is we did the exact same thing on the SSL TLS stack, which is owned by ARM, which is named is ARM Embed TLS. Here you have a complete report. If you follow this link, which is going, this is like a roughly a bit more than a 100-page document, which explains how we were able to generate the same level of trust in an SSL TLS stack. And here the NIST in a report in 2016 highlighted our ability to conduct such tests. So we do that on many different kind of code. Typically it can be super low level code. Here for instance we did the exact same thing on the GoodX driver, which actually manages a touchscreen, and definitely is very critical if you got a module of a Linux kernel which can crash, because the whole system could crash. And here we can have a mathematical guarantee that whichever value is actually written by the hardware, never ever the driver is going to crash. We did the exact same thing in just 1.5 hours on a driver from ST Microelectronics on an accelerometer. Here you can have a look at this on the GitHub. You got the source code. Just a quick last slide to finish this talk is indeed, if you want a live demo, do not hesitate to reach out to us, contact at TrustInSoft.com, and we will be happy to give you a more extensive demo of our capabilities and how we can help you deliver high quality code. And if you wonder about how does that fit in a continuous integration process, so here you got the developers, and here you have the nightly builds. Generally, there are, I would say, two places in the CI/CD process where our customer uses. First one is when the developer pushes his or her changes to the source code source control server. So generally, this is implemented as Git hooks, or during the build time at night. So generally this is coupled as a Jenkins plugin. Thanks for listening to me, and see you soon.